Hi guys, so firstly let me apologize for how things have gone the last couple of days. First there was the sound issue, then there was the first there was the lack of slides issue, then there was the lack of slides and sound issues. I think we've got those sorted out now. So here is the Pigeonhole Principle, take 2. Okay, so just a reminder of the Pigeonhole Principle, or if you're not in the advanced group and you're watching this on YouTube, imagine you play 8 games of soccer. Then the Pigeonhole Principle is the principle that says 2 of them must occur on the same day of the week. What's the reason for this? Well, really it's that there are more games of soccer than days of the week. And if you try to pair them up, you're going to be left with something over, and you're going to have to put a second one in there. More generalized Pigeonhole Principle says that, look, if you play 15 games of soccer, or 7 n plus 1 games of soccer, you will need to have 3, or n plus 1, games on the same day. Another way to think of it is the average number of games you're playing on a particular day of the week is 8 out of 7 in this example, which is a little bit more than 1.142857, and you should know recurring numbers. If you don't, talk to the algebra guy. Anyway, this is more than 1, and therefore at some point it must be 2. Because if it was always 1 or less, you would never get an average over 1. So here's a fun application. There are 2 people in Pretoria who have exactly the same number of hairs on their head. How do I know this? Well, I know that there's an upper bound on how many hairs people have on their heads. Okay, this isn't a mathematical truth, but in the same sense as humans do not grow to 20 feet tall, or 20 meters tall, or whatever you want, they do not grow billions of hairs. I think this upper bound is a few 100,000, and the number of people in Pretoria is a few million. So there are more people in Pretoria than there are possible numbers of hairs one can have on their head. And therefore, by the Pigeonhole Principle, you must have 2 people who have the same number of hairs on their head in Pretoria. Okay. So secondly, in any group of n people, 2 of them must share the same number of acquaintances. Now we have to be a little bit careful here. In this example, acquaintanceship works on the Facebook principle, not the Instagram principle. So on Facebook, if I'm friends with you, you're friends with me, and we both know each other. On the other hand, on Instagram, I can follow you without you following me, or you can follow me without me following you back. So friendship there is not symmetric. But on Facebook it is, and that's what's meant in this problem. Okay, well, how many friends could one have here if there's a group of n of us? Well, you could know no one else in the group, that's 0. You could know 1 person, 2, 3, 4, all the way up to everyone, which means n minus 1 people. So you know everyone except yourself. Okay, so that's n people and n values. This seems like it might be possible. Right, maybe one guy knows 0 people, one guy knows 1 person, one guy knows 2 people, one guy knows 3 people, all the way up to one guy who knows all n minus 1 other people. Okay, so we can rule this out. Okay, that's the only way it could happen though. And we can rule that out by look at the guy who knows everyone and the guy who knows no one. Ask, do they know each other? Well, if they know each other, the guy who's supposed to know no one knows someone, so that can't be right. If they don't know each other, the guy who knows everyone doesn't know someone. And so that's a contradiction either way. And therefore, yes, it is in fact true that 2 of them have the same number of acquaintances. Okay, here's a slightly more involved example. So let's have an n greater than 10, even equal to 10 is fine, and s is is a subset of the numbers 1 through n squared. So if n is 20, s is a 10 element if n is 20, then s is a 20 element subset of 1, 2, 3 up to 400. Okay, and the claim is that there are two subsets of S with the same sum. I know it says in there, it's a misprint. Okay. Well, how many subsets does S have? 2 to the n. Okay, and how many possible sums could a subset of S have? Well, it's got to be at least 0. It's got to be a whole number. And it's at most n times n squared, right? Take the biggest possible numbers in S, and they're n squared, and n squared minus 1, and n squared minus 2. And you add those up, and you get something which is about, but maybe a little, well, is a little bit less than n squared times the n elements. So you're somewhere between 0 and n cubed with your subset sum, and you have 2 to the n subsets. Now when n is big, and in fact in this particular case big is bigger than 10, 2 to the n is bigger than n cubed. Okay, so 2 to the 10 is 1024, n cube's 1000. When n's 11, it's 2048 versus 1331. There are more subsets than there are possible subset sums, and therefore two of them are going to match up. Okay, so here's a nice question. We're going to 3 color points in the plane and prove that 2 of the points are the same color unit distance apart. This involves a very interesting construction due to Mossel. Don't ask me anything else about him. And now I can actually draw it. Well, hopefully. Okay, so we draw equilateral triangles. Okay. These are equilateral triangles. And we're going to have 7 points, which I think is this. Okay, these, oof. Well, these 7 vertices are points. I'm going to just draw, hope this works. So there's a red point here. These two have to be different points, so different colors. Let's call them blue and green. Okay, so that one's going to be green. This one has to be red. And these two have to be blue and green again. And therefore this one would also be... these two have to be blue and green again in some order. And now we've constructed it so that this distance is 1, 2. But this now has to be red, but it can't be red, so we get a contradiction. Okay, and I know that was ugly, but it's better than not having any view of this at all. Okay, I know that looks pigeonholey, turns out this one wasn't. Okay, so here's a very nice question, which apparently was given to given by Euros to all of his prodigies, and the bright ones solved it and became prodigies, and the less bright ones didn't and went off and did something else. Less bright maybe isn't the right word. Maybe they were interested in other things aside from mathematics. Can't help tastes. Okay, so how many integers are there that you can take from 1 through 2n without getting one which is a multiple of another? Well, you can do n. You take n plus 1, n plus 2 up to 2n. Okay, how do I know that none is a multiple of the other? Well, I can double the smallest one, which is n plus 1, get something bigger than the biggest one, which is 2n plus, well, it's 2n, and therefore no doubles in that set. Now, is it true that you can't take n plus 1? Maybe if we were cleverer we could. But it turns out you can't. So what you do is you write every integer here as an odd number times the power of 2. Okay, there's one unique way of doing that for each number. Okay. How many different odd numbers do you get? Well, n, right? 1, 3, up to 2n minus 1. Okay, so if you take two numbers which have the same odd, one's going to be a multiple of the other. So if you ever take n plus 1 numbers, by the pigeonhole principle you must take two with the same odd number, and then one will be a multiple of the other. Okay, so notice how we've gone from 8 days of soccer to this very intricate argument where you write things as 2 to the n times an odd. Okay, let's do an IMO question and prove that every set of 10 two-digit numbers has two disjoint subsets with the same sum of elements. And this is very much like the problem we just did. You've got 10 two-digit numbers. They must, well, there are 1024 possible subsets. And how many sums could they possibly have? Well, the smallest you could have is 10 plus 11 up to plus, well, the smallest you could have is the empty set, so 0. The largest you could have is 90 plus 91 plus 92 up to 99. That's a bit less than 1,000. 945 or something. Okay, so once again, there are more subsets than there are possible subset sums, and therefore, by the pigeonhole principle, there are two subsets with the same sum of elements. Wait, it says disjoint subsets. So we've shown that there are two subsets, but maybe they're subsets which have an overlap. Okay, remove the overlaps. And we are done. Right, just if something appears in both of them, just subtract it. Okay, here's a nice one. It's the Fibonacci numbers. And because it's the year 2021, we're going to show that there is a Fibonacci number which ends in 2021 zeros. Which effectively means it's 0 mod 10 to the 2021. And in fact, you eventually find a number which is 0 mod anything in the Fibonacci numbers. So, stronger claim. How do we know that? Well, the first thing is that notice that the Fibonacci numbers are going to be cyclic mod k. Okay, if I know two of them, everything's determined. For a pair of adjacent Fibonacci numbers, mod k, there are k squared possible things, so you'll eventually get to the same thing again. Or eventually you'll get to, starting somewhere, you'll get to the same thing again. They also have the nice property that they go backwards, which is enough to get you the cyclic nature of them. Okay, so they start 1, 1, but that means the thing before that 1, 1 is actually 0, and 0 mod anything. And it's cyclic mod 10 to the 2021, so eventually you get to another 0, mod 10 to the 21, and you have a Fibonacci number that ends in 2021 zeros. Or 10 billion zeros if you want. Okay, so now I'm going to talk about something called the probabilistic method, which is a hell of a lot like the pigeonhole principle. This was popularized by Erdos, who really made his career out of it. And, Erdos had one of the more illustrious careers in mathematics. So there's something going on here. And it's the idea that you want to show some structure exists. You show that on average, okay, and I'm going to talk about what that means in a little bit, more than 0 such things exist. Okay, so when I say on average, you make a whole collection of things like this. Well, you want to show a structure with a particular property exists. So you make a whole bunch of structures and put a distribution over them. And you then say, well, how many of these things exist on average, and if it's more than 0, there exists at least one. So here's an example. We have a thing called a tournament. And a tournament is going to be a kind of directed graph where every pair of vertices has exactly one edge between it. Okay, so for example, 4 of you are going to play ping pong with each other. Someone beats someone else. Or each of you is going to play a game. Someone's going to win, someone's going to lose, and if A beats B and B beats C, that says nothing about what happens between A and C. Okay, so we're going to say a tournament has property SK. If for every set of K players, there is some player who beats everyone. Does there exist a finite tournament with property SK for every K? Okay, so let's say n equals 5. Does there exist a tournament where for every group of 5 players, someone beat all of them? Now, this was asked to Erdos in, I think, 1936 by some very respected graph theorist who'd been battling to construct a whole family where it always works, and he really had, serious trouble with it. This is a difficult problem even for professionals. Okay, so Erdos was like, okay, let's generate a random tournament. So forget about, a table tennis tournament where some people are actually better than each other. Everyone just shows up, flips a coin, decides who wins. Okay, so now this, so Erdos said, alright, let's say we've got K players. What's the probability that no one beats any of them? Well, what's the probability that Bob doesn't beat all of them? And then there are n minus k people outside this particular group of n players. So we'll just take that to the n minus 1. Sorry, n minus k. And the probability that Bob doesn't beat all of them is 1 minus half to the k. Okay, now there are n choose k such groups. And there's some correlation, but the probability of the union of all of the probability of the union is less than the sum of the probabilities. So the chances that every group of K players has no one beat them is n choose K, or is less than n choose K times this whole thing, which for large n turns out to be less than 1. In fact, for very large n turns out to be a whole lot less than 1. It tends to 0 if you keep K fixed and grow n. So what Erdos said was, you might be having a whole lot of trouble constructing particular examples of this, but if you go large enough, it turns out basically all of them do. You don't have to. Okay, that's quite a powerful result. Yeah. Now the reason this feels weird is that, for tournaments where skill does matter, the very few tournaments which look like actually this guy is a lot better than this guy and things are different, those are the ones we intuit, and therefore those are the ones which we naturally think about, and they're almost the only ones without this property. Okay, so let's talk about a geometry problem. Alice will choose 10 points in the plane. Bob is going to try and cover them all with non-overlapping unit disks. Okay, so you can think of this as Alice puts down 10 points on a really infinitely large table, and Bob tries to put coins over them. Can Alice stop him? Look, if she puts them far apart, he's just going to put a coin over each one. If she puts them all really close together, bunches them up, Bob will just put a single coin over all of them. But maybe if she puts them just at like 1.1 away from each other and something like this, she can actually stop him. Now, 10 really does matter here. If we only gave Alice 1 point, Bob will just put a coin over it. If we gave her some ridiculous number of points, okay, put down 10 to the 1,000, Alice can make a very fine mesh over a whole big area, and Bob's just not going to be able to put down the coins without having a little bit of space in between. Okay, so Alice needs to play at a meso level, okay, making things like 1.1 or 0.52 or 0.49, something like this apart. Okay. So let's go through some small cases. Okay, so in the case where of 3 coins, well, if 2 of them are within 2 of each other, Alice can just put down a single coin, and that will be enough to cover those 2, and then the last point is just outside of this 1 coin, and somehow Alice is going to be able to finish it. Now, for 4 coins, you have to do a little bit more casework. Are there 3 which are in the same area? If so, put 1 down. If not, well, are there 2? Put something around that, and then you make some case argument about the other 2. 5 coins gets harder. So I once asked this to a friend who's, was quite a distinguished geometer, and she went to a conference and came back to me sort of a week later going, yeah, I was at this conference last weekend, and there were like 5 or 6 of us sitting around talking about it, and we're convinced we can do it for 5 coins. This idea is not going to get us to 10. Okay, doing very caseworky way or trying to construct it. But this is a Pigeonhole Principle lecture, so let's see what we can do. Notice that the efficient packing covers pi over square root 12, or if you're not completely evil and use tau instead of pi, tau over 4 square root 3, or tau over square root of 48, which works out to about 0.90 something. Okay, so if I'm going to throw down the efficient packing, okay, and you can shift things around, so it's actually a random efficient packing, you'll hit on average a little bit over 9 points, and that means sometimes you're going to hit 10. If you try to use this argument with 11, it doesn't quite work. You get that you cover like 9.03 or something. Okay. But some covering like this will get you to 10. Okay, that begs the question, or raises the question at least, how many points can you always cover? Well, this is open. So if you can solve it, or even make some progress on it, that's a paper, and quite an impressive one. And even if you have some ideas, come talk to me, we'll talk about it. Okay, so upper bounds, Kiyome, Okiyama, and Uhara, I hope I pronounced those right, found a configuration, I think in 2014, of 53 points which can't be covered, so at most 52. 12 points can be covered, a result of the famous Peter Winkler, who's at Dartmouth. And I think he used something very similar to the argument we used. He just said, well, not only are you going to shift this thing, but you can also rotate it, and I know something about how much variance there has to be here, so I can, he managed to claw his way up to 12. But still, we're between 12 and 52, so if you can prove it for 13, we're doing pretty well. Suspected it's sort of somewhere around 30, but who knows. Everything else is open. Okay, and that is my talk, and apologies again for everything that